Lecture 5.3, Polarization. The first thing that we got to talk about is how is energy transferred by electromagnetic waves? How is energy transferred by electromagnetic waves? So we should think about a picture. So when I say how is energy is transferred, I'm really asking that the sun does this on a daily, oops, that didn't look good, daily basis. How does it do it? So the easiest way to visualize this is that visualize this process using plane waves. It's just easier. So you could imagine that you have something like this. So I have a wave, and the way I'm going to look at this wave is I'm going to look at this as a sheet. So you could imagine that this is my sheet right here. So now I have a series of sheets. And you could imagine then, as all these sheets are being transmitted, they are electric and magnetic fields. So in this plane, I'll say that this axis, this will be the electric field. And then in this direction, this will be the magnetic field. And then we imagine here is that this is the direction of the wave. So then if I look at this in terms of an axis, you could imagine here that if I use my axis as I did before, this is the y direction, this is the z direction, and then this guy here is the x direction. So I'm seeing these sheets here. Now the intensity of a wave depends only on the amplitude of the electric and magnetic field. So the intensity of a wave depends only on the amplitude of the wave. So then we typically write intensity with the symbol I, and this guy is the amplitude squared. So, I mean, this makes complete sense. The reason why this makes complete sense here is because you could imagine that if you have larger waves versus smaller waves, larger waves have more of a punch, right? They have more of a punch. And that's because they are more intense. So if you have a bigger amplitude, then I'm going to have more of a punch in the wave, and therefore we say it's more intense. If it's smaller amplitude or smaller waves, they have less of a punch, so therefore they're less intense. So physically, it makes sense that way. But that's not the way we typically see waves. So although plane waves are easier to visualize, the transfer of energy spherical waves are what we see. And here's a good example. And so what I see here so if we drop a rock in flat water, what you're seeing here is that when you drop it right at that spot, this is the source of the waves. And what happens here is that what goes out here, this is the wavefront that emanates from that point here. So what we're seeing here is that a rock dropped in water has wavefronts that are spreading out spherically. The same thing happens with the light bulb now. For a light bulb, the wavefronts spread out spherically. So if I was to draw a light bulb, let's say that here's my light bulb. And then we know that the light bulb has that part that we screw in. And then this is the guy that kind of goes into the socket. So this produces light, right? And then we have the metal part that screws in. And then this is where it sits here. So when I'm looking at waves here, what am I actually seeing here? There are wavefronts that are spreading out as they go out. So when you start to look at the intensity of these lights, the intensity clearly has to be proportional to the area, what location you're actually looking at. So the way we can look at this intensity here is that we could say here that the intensity strength changes with distance. From the source. So by definition, intensity is actually equal to power, the rate of energy per unit time, that's deposited in at some area. So if we look at this as a spherical wave, then this is 4 pi r squared for the area, and then we have the power, and we see that this is proportional to 1 over r squared. So if I look at that power, then I could imagine that I have a wave that's spreading out. So if I look at this, if I have this image right here, you could see that these are spherically spread out waveforms. So if this is my center, then I know that it's emanating from this point out spherically. And so I can look at two different points. I could look at point 1 right here, or I could look at point 2 out here. So at point 1, we see that this is closer to the source. And if you're closer to the source, this is clearly a smaller distance. And if it's a smaller distance, it must have a higher intensity. Now I'm running out of space, so I'm going to move this over here. Okay. So if I move this down right here, if it has a higher intensity, which really tells us that because it's proportional to 1 over r squared, that this intensity is large because the distance from the source is small. On the other hand, if I look at point 2, this is farther from the source. So therefore, this has a larger distance, and therefore it has a lower intensity. So if I look at its distance dependence, that's going to be large, so therefore the intensity has to be lower. So what we want to do here is that now we want to focus on applying intensity to light polarization. So here we go. Light polarization. Polarization is a characteristic of transverse waves. And electromagnetic waves are transverse. Why is that? So let's imagine that we have, this is the direction of motion. So this is telling me that this is the direction of the velocity. So when I look at my waves, I see that we have two perpendicular components. We have the electric field. And so what this is telling me is that the electric field is perpendicular to the direction of motion. And then these guys are perpendicular also to the direction of the wave. And then this is my magnetic field. They're perpendicular to the velocity. That's what we mean by a transverse wave. Now, linear polarized waves have amplitudes that point in a particular direction. So these waves point in a particular direction. So let's imagine that we have a plane. Okay, so let's look at this here. So I imagine that I have a plane here. And if I look at this plane, I'm going to look that this guy is this yellow plane right here. And so what I'm going to see here is that I have an axis that goes like this, which is the y-axis, and then I have an axis that's perpendicular to that, and that's the z, and then this direction right here is the x direction. So if I look at a wave here, this wave is oscillating in the y direction as the wave speed is moving like this. This is what we call, in this situation, I would call this vertical polarization. Because the y amplitude, the wave has an amplitude only in the y-axis. Now I can do the exact same thing here. And so now what I'm going to do is that I'm going to create a horizontal plane that looks something like this. And then I have my axis again. So here's my y-axis. And then here is my x-axis. And then here is my z-axis. So when I look at this wave, I can then say that this wave can be oscillating along the z-axis when the wave is moving in this direction right here. This is what we call horizontal polarization. Now, to simplify the notation, it's common to draw the oscillating amplitudes with a single vector. In other words, if I have a wave that goes like this, it's vertically polarized. This is an oscillating vector field. Excuse me, an oscillating vector. It is a field, but I should have just said vector. So then this guy looks like this, and I'm going to say that this amplitude is in the y direction. And if I have a wave that's oscillating horizontally like this, then we then define this as a horizontal amplitude that is also oscillating. Now, what I want to do here is that I want to share an image with you so you could see what I'm talking about. And this is right out of Wikipedia. So if I come into here, you could see that this is the oscillating amplitude right here. So it's going back and forth, but it's one arrow, and that's the direction of the polarization. So coming back to this here, let me make sure I'm on the right window. I am. So what I just showed you here is that this was polarization video, or it's a GIF, 1. That's the first one. Now, what about unpolarized waves? So, unpolarized waves have multiple directions of their oscillating amplitude. Circular polarized waves can be decomposed. And when I say decomposed, that means broken into vector components. So picture-wise, I imagine something like this here. So now let's say that I have an axis that goes like this. And again, I'll keep with my same axis, which is a right-hand axis. Oops, that's an X. And what I imagine here is that I have a polarization that's going to go something like this. So if I look at this guy, it's following a circle like that here. So what you're seeing here is that that is the direction of the wave. And here, this is called circular polarization. Even though I said unpolarized, you'll see what I mean by that in a moment. Now, the way I can redraw this here is that I can draw it the following way. I'm going to set up my axis again. And what you're seeing here is that there's a mixture of two states. So one state here has my oscillating field going up and down, which is now AY. Then I have a second field that's oscillating in this direction, which is AZ. And if I look at this from the front view, so if I have a front view of this situation, what I see here is that I'm actually seeing this go in a circle. And the front view then looks like this here, where this is AY, and of course this is AX or AZ. But the way we draw it is that we drop all of the notation and just say that this is a mixture of polarizations, of two polarizations. Now, that's what I have for circular polarized. And I'll show you a video from Wikipedia again that actually does a really good job. So what you're seeing here is that, look what you find. You're seeing that I have a circular polarized wave, but I can decompose it into a vertical and a horizontal process. Okay. So coming back to my screen here, here's what I have. So by the way, this is the Wikipedia one. This is, let me just copy this guy just to be quicker. I'm going to copy this guy. Then I'm going to paste this guy right here. And I'm going to call that two. Okay. So now what we want to think about here is that most light, as we'll see, is unpolarized and not circularly polarized. And we're primarily going to look at unpolarized light, but I wanted to show you circularly polarized light before we move on. Okay, so now here's what we want to do. A mechanical filter removes components of a wave. And in optics, what we do here is that we call this a polarizer. So here's what we find here. So a mechanical filter is really, it acts sort of like a picket fence. So now if I look at circularly polarized light, here's what we're seeing here. So we know that if I have an axis like this, and I'm sending in circularly polarized light, it's going to do something like this here. And remember, that's not the way we draw it. So the way we draw it here is we now have this like coming like this. So it has a Y component, a vertical component, and it has a horizontal component that looks like this. So because I have this circularly polarized light, I can decompose all of those in terms of these two components. Now what we're going to do here is that this light is moving to the right like this with some wave speed. And now what I'm going to do here is I'm going to construct a barrier or a filter or a polarizer. And so what you're seeing here is that you're seeing this here. So this is my barrier here. And so as this guy is coming through, what you're going to find here is that it filters out. So by the way, so this is my barrier. And this is what's called a vertical polarizer. And you could see the reason why they call it vertical is because the slit is up and down along the y-axis. And so as a consequence, the only thing that goes through here is the vertical ones. So here what you do is that you start with circularly polarization, and then you end with vertically polarized light. In other words, what we're seeing here is that the vertical polarizer filters out the horizontal component. And again, here's a very nice image from Wikipedia that looks like this. And what you're seeing in this image here is that look what you're getting here. You can see that right here, This guy right here, you can see here, this is circular polarization. And then what you're seeing right here is that this guy has a barrier that looks like this here. It turns out that it has, I think that's a horizontal one. So I got to redraw this. So if I look at this, it looks like this here. And you could see that there's a hole right there. But there's a barrier horizontally that blocks all of the vertical. So what you're seeing here is that then this guy here filters out the vertical component. Because what you're left with right here is you have horizontally polarized waves. That's what we're seeing right there. So we don't really want to get attached to this picture because the picture does not apply to electrical.